Welcome, friends. In the last lecture, we have seen the various aspects of capacitance graded cable, where we have seen a central core, and surrounding to that core we have n number of different dielectric mediums, and there we have seen that maximum stress is not necessarily occurs on the conductor surface. It may also occurs on some dielectric interface, depending on the values of different relative permittivities of the different dielectric mediums. Now, presently we will shortly start the capacitance of now 3-core cable. Now, what is 3-core cable? Now, it's simple. It is 3-core cable. What is that? Means 3 conductors. 3 conductors separated by some dielectric medium. Okay, separated by some dielectric medium. You can say that a 3-core cable is roughly assumed by this model. You see, these are 3 wires. These 3 are wires. Now, one conductor, each wire is carrying one conductor, and each conductor having a dielectric medium, right? So, if they are arranged in this fashion, that means they are arranged at the vertex of an equilateral triangle, then this arrangement roughly you can consider this model a miniature version of underground cable, 3-core underground cable. Of course, we have many more outside layers to protect the core from moisture and several other factors. These 3 conductors, roughly you can say that the conducting part, the miniature version of and 3-core underground cable, and of course we have these 3 conductors, and surrounding to that this finger, this is the intersheath. Okay, this is the intersheath, right? So now what will be the equivalent circuit? So we have these 3 conductors. We have these 3 conductors. This is conductor 1, conductor 2, conductor 3. Preferably they are arranged at the vertex of 3 equilateral triangle. Now, the conductors are separated by an dielectric medium. As I told you, again I am showing you. You see, if this is these are the 2 conductors. These are the 2 conductors. You see, this green portion and the red portion is the insulating material. Okay, so you see these 2 conductors. Okay, this you see, this is the conductor, right? And surrounding to that conductor we have a insulating layer. So these 2 conductors are separated by a dielectric medium. So we can say that we have a capacitance formed between any 2 conductors. So that capacitance is called core capacitance, CC. So in this way we have got 3 core capacitances. And similarly, if again I am showing, if this is the 3-core cable and surrounding to that we have a sheath like this. Now from each core we have another dielectric medium up to the sheath. So this up to this position, let us say up to this position, from the conductor to my finger, up to my finger, we have another dielectric medium. So again, another 3 sets of dielectric medium forms or capacitances form, that is called CS. It is called sheath capacitances. Okay, we have sheath capacitances. So we have 3 core capacitances, CC for core capacitances, that is the capacitance formed between any 2 cores. And we have 3 sheath capacitances, that is capacitance formed between any core sheath. So this outer circle, it's called sheath. this outer circle is called sheath. This entire outer circle. Now what will be the capacitance to neutral? What is capacitance to neutral? Capacitance per phase. That is the next question. Let us solve. Try to find out the answer. Now Cn, that is the per phase capacitance, is given by this formula, Cs plus 3Cc. How? Now you see this this is the original diagram which is shown previously in the previous slide. Now you see these three capacitances are forming a delta. Now if you can make, or if you can convert this delta into star, so this formation will be formed. This is neutral point, and this is also, you can say, ground, that is sheath is always grounded. So when the three capacitances, same values capacitances, it is converted from delta to star, it becomes 3 times. Each capacitances becomes 3 times. And we have a core at this point. We have a core at this point. This is the conductor. And it is this point is used by blue. It is actually neutral point, not red. Red dots are core, and blue dots is the neutral point. Okay. So with respect to each core, we have one path along this path, and we have another along this path. So with respect to this core, if you form the per phase capacitances, so basically two capacitances, that is 3Cc and Cs, are forming parallel. So basically the neutral capacitance is the 3Cc and parallel to that Cs, because they are two parallel paths. So if if two capacitances are parallel, their equivalent capacitances are summed. So the per phase neutral capacitance is 3Cc plus Cs. This is the answer. Now the next question comes, what is the value of the Cs and Cc? What is the value? What is Cs and Cc? We understand that is Cs is the core capacitance and Cc is the core capacitance and Cs is the core capacitance. But what is the value of Cc? How do you measure? How we can measure these values? That is the next question. So let us first find out how you can measure Cs. The first method, there are two different methods by which we can measure Cs. You see the three cores bunched together, and the capacitance C1 is measured between bunched core and the sheath. That means we have a capacitance measuring device. We need to fix the capacitance measuring device at these 2 points, one across core and another across sheath. So this is the measuring device by which you can measure capacitance. So whatever data it shows, let us say it is showing C1. So basically you see this C1 is basically with respect to these 2 points, there are 3 different parallel paths. Because you see C, these are same point. Because it is grounded. See, these are same point. So this point are all same. So with respect to core and this sheath, we have three different parallel paths. So whatever we have measured C1, if we fix a capacitance measuring device and if you fix the two lead across these 2 points, so we will basically have three parallel paths. So three parallel path means it is 3 times. So core capacitance is basically whatever data it is showing, it is 1/3 of that data. It is the not core capacitance, it is the sheath capacitance. Now what is the meaning of this statement, 3 cores bunched together? Now you see, again I am showing, again you have these 3 cores. Now assume I have destroyed the insulating part as this is the case. You see the conductor is exposed. Likewise, we have, let us say we have destroyed the insulating part of these these 2 remaining pores. So if we destroy the insulating part, then what will happen, this conducting part will come direct in touch with each other. That is the meaning 3 cores bunched together. That means you are bunching them together. So what will be the immediate consequencing of that? If 3 cores are come in touch with each other directly, then that CC, that means the core capacitance between each 2 cores, will be destroyed. Because no such dielectric medium is in between, so there is no chance of forming CC, that is the core capacitance, right? So due to this fact, in this diagram, there is no CC. There is no CC because they are simply washed out because we have destroyed the insulating part. So this is how we can measure the CS. That means first we will measure bunch together. That means 3 cores will be now forming a same single core. And the capacitance is measured between one lead is placed at this point. This is the lead number 1 of the measuring device and this is the lead number 2. Lead number 2 you will fix at the sheath. Whatever data you will give in C1, that C1 should be divided by 3 to get the sheath capacitance. This is how you measure the sheath capacitance. Next, by how you measure the CC, core capacitance. Now this time you need not bunch 3 cores at that time, you should bunch 2 cores. You should keep 1 core intact. You see, these 2 cores, these were the 2 cores are bunched. You see, this CC is wiped out. So that is not shown because this core, that means conductor core number 1, core number 2 and core number 3. These core 1 and 2 are bunched together. Not only that, they are bunched together, okay, but along with the sheath itself. So these 2 cores will be bunched, okay, that is fine, but you should take the along with the sheath itself. That means, again I am showing, suppose this is the 2 conductors are bunching. Now whatever be the whatever be the intersheath, so this intersheath, that is the this dielectric medium I should destroy. So that conducting path is in direct contact with each other, that is okay. In addition to that, this conducting material now come in direct contact with the sheath also, as I have removed or I have destroyed this insulating part. So this is the equivalent diagram of this. So this is 1 core. Now conductor 1, core 1 and core 2 becomes the same core, and the conductor 3 or core 3 is the healthy core. Now with respect to the measuring device should be you see the capacitance C2, that is the data, is measured between the remaining core and the sheath. So you should keep your measuring device at these 2 points. This is the measuring device The lead number 1 should be placed at 4 remaining core and lead number 2 should be placed seed. Now with respect to these 2 points, you see again 3 parallel paths, 1, 2, 3. 3 parallel paths from conductor to seed. So one is CC, another one is CC, another one is CS. So altogether, if it is measured C2, then C2 is roughly C2CC plus CS. So from there, you have already known what is CS. So CC should be is equal to C2 minus CS by 2. So in this way, you can evaluate both CC and CS. Now we will solving one problem on this. Now we have a 3-core cable is measured as found. Now you see what is the statement. Capacitance between 3 cores bunched together and the sheath is 7.5 microfarad. That means this example. So this is C1, it is measuring. So C1 it is measuring equals to 7.5 microfarad. So from there you can straight write CS is equal to C1 by 3, that means 2.5 microfarad. Second part, you concentrate the B part. Capacitance between the conductor and the other two connected together to the sheath is 4.5 microfarad. That means it is clearly indicating C2. C2 is 4.5 microfarad. What is C2? C2 is 2cc plus CS, which is equal to 4.5. So from there you will have CC as 4.5 minus 2.5 divided by 2, that will be 1 microfarad. So you will have per phase capacitance, that means 3cc plus CS, which will be equal to 3 into 1 plus 2.5, that means 5.5 microfarad. So first part is gone, capacitance to neutral. And total charging current, so you will require charging current, okay, IC. So total charging current, sorry, not charging current, it is asked to evaluate charging kVAR. Okay, so you have V, so you have 11 kV, so per phase is 11 by root 3, right? So charging kVAR, which is equal to from there, what will be IC? You know, V phase, that means 11 by root 3 into omega C. Omega C. So omega C, that means equal to 11 by root 3 into 314 into 5.5 into 10 to the power minus 6 in amperes. Now the charging kVAR Q, that means equal to root 3 into 11 kV, that multiplied by this current. I do not have the data with me right now, so it will be kVAR. So I want you to solve this. So this is the problem. This is how you solve. Now last topic is dielectric laws. Now what is meaning by dielectric laws? Suppose we consider a very simple model of underground cables. Let us say this is the core having radius r and this is the sheath. This is the sheath. Okay, having radius capital D. Now this medium is filled with dielectric material of epsilon, some value, okay, epsilon r. Right. This medium is filled with a value epsilon r. Now ideally, as you can see, this is voltage given V and this is grounded. So ideally this is separated by a potential distance, that means this surface and this surface. So roughly you can say, you can think this model as a capacitor like this. You can say this model as a capacitor like this. So whatever current is flowing through this capacitor is called charging current. That charging current should lead this voltage by an angle of 90 degree. This voltage by an angle of 90 degree. This is the property of capacitance. This is the ideal case. But practically you have a insulation resistance. So a small leakage current will flow through this insulation resistance, right? A small leakage current. Let us say that small leakage current is IL or I leak. So this I leakage current should be in phase with V. So as a result, what will be the resulting current flowing is this. And this delta, this angle is called delta. This is called loss angle. This delta is called loss angle. It is typically in the range of 0 to 3 degree, roughly. And due to this resistive path, a loss will incur. That is called dielectric loss. So for an underground cable, if the delta value is small, that indicates that your dielectric medium is in good condition. Ideally, it should be equal to 0. There should not be any leakage current. However, practically it is not possible. So whatever with a very small leakage current will always flowing. So due to that fact, this delta will be always having some angle, very small angle. So if that delta angle is very small and close to 0, then the dielectric medium is in good condition. The more it is close to 0, the better will be the dielectric medium. If delta starts increasing over the time, that means your dielectric loss, that means the leakage current will be more. If the if some after certain time, if this delta current is this delta 2, then leakage current is again more. So that means your dielectric medium having some loss through insulation resistance. So it should not be the case. Okay, so if delta start increasing, then a preventionary measure should be taken. So ideally delta should be always equal to 0, but if it is within the range 0 to 2 degree, it is acceptable. However, it should not go beyond that. If it is go beyond that, then it is not accepted. Now with this, I am coming to the end of this underground cable. So in this lecture, we have first seen the 3-core cable, where we have seen how you measure core capacitance and sheath capacitance, which is intrinsic in nature. Then from there we have solved a problem, and we have also understood the concept of dielectric loss. It is due to the insulation resistance that is occurred in between conductor surface and the dielectric medium. So with this, I am ending the underground cable chapter. From the subsequent lectures, I will start some new chapter. Thank you.